Students, this is the last segment of lecture 1. Hope you've understood all of the topics of the previous segments. In this segment, we are going to discuss on difference of sets, complement of set. We'll see proof of some identities and we'll know about De Morgan's law and see its proof. And at last, we'll solve some problems on generalized union and intersection. At first comes difference of sets. Let's assume two sets A and B. Difference of A and B is denoted by A minus B. It is also known as subtraction from A to B. So A minus B is a set. A minus B is a set that contains all of the elements which belong to set A and do not belong to set B. That means all of the elements of A minus B will be the elements of A which do not belong to B. So if someone claims that X belongs to A minus B, it means X belongs to set A and X doesn't belong to set B. So we can see an example here that, for example, set A is 4, 9, 16, 25 and set B is 16, 25, 36, 49. So if you have to determine A minus B, then you'll have to recall the definition, and here we can see that A minus B will contain all of the elements of A which do not belong to B. Here we can see that 16 and 25 are common in both of the sets. So A minus B will contain 4, 9, but it won't contain 16 and 25. You can ask something whether we can take 36 or 49. Can we? No, because X doesn't belong to set B. So A minus B here is 4, 9. We can see another example here. For example, C is a set X, Y, Z, and D is a set A and B. Here, if we have to determine C minus D, we see here that none of the elements of C are common to D, any of D, right? So we can take all of the elements of C and we cannot take any of the elements from D. So this is C minus D. Can we determine D minus C here? Yes. So in this case, all of the elements of D will be contained by D minus C and none of the elements of C will be taken, right? Okay, so this is how we determine A minus B, and we can see the Venn diagram presentation of difference of sets. Here, if a set is A like this and the set is B, we know that this is the intersection of these two sets. According to the definition, can we take any of the elements from this whole B? No, because X doesn't belong to B. And can we take any of the element from this whole A? No, we cannot take the elements from the whole A, but we can take the elements from this blue shaded regions. And why not this intersection region? Because if we would take any of the elements from this region, it would also belong to B, but from the definition X cannot belong to B. So this shaded region in blue, this portion represents the set A minus B. Okay, this is all from difference of sets, but now we'll know about complement. the next topic, complement. And complement of sets is very much related to difference of sets. Complement. Okay. So let's assume a set A for which the universal set is U. This is universal set. Complement of set A is denoted by AC, right? Complement of set A is denoted by AC, and the set AC refers to a set that contains all of the elements of the universal set U, but none of the elements of set A. I repeat, complement of A is a set which contains all of the elements of universal set, but not any of the elements from A. So by definition, complement of A equals to U minus A, right? So if someone claims that X belongs to AC, it means X belongs to U minus A. That means X belongs to U and X doesn't belong to set A, right? And this is what we actually told in our definition, right? X will belong to U and X cannot belong to set A. Okay, so we can see some examples here. For example, for some set under consideration, U is 1, 2, 3, 4 till 10, and A is the set of all even numbers up to 10. 2, 4, 6, 8, 10. So if we have to determine AC, we'll have to determine U minus A. It means 1, 2, 3, 4, 10 minus 2, 4, 6, 8, 10, right? So as we have learned in difference of sets, AC will be having all of the elements of U except all of the elements of A. So AC will contain 1, 3, 5, 7 and 9, and none of these even numbers, right? So this is complement of A here in this case. So we can clear our concept by seeing a Venn diagram representation to this complement. Here, this is U, the universal set, and this is set A. If we have to determine AC or complement of A, can any of the elements of AC, belong to set A? No, it doesn't belong to A. And any of the elements of AC will belong to universal set, that is U. So this region, which I have shaded in blue, this shaded region which is in blue refers to or represent the set complement of A, or this is U minus A. So this is how we represent complement of set A. So now I'll prove some identities, and as we know there are many identities in set theory, and we can study them from the book of Kenneth H. Rosen, and the book's name is Discrete Mathematics and its Application. We can solve some problems as well of set theory from that book. So at first I'll start with the statement. We'll prove it first, and we'll prove it using Venn diagram. This is set A, this is set B, and as we can remember from the definition of A minus B, this black shaded portion represented A minus B. So to prove A minus B to be equal to A intersection B BC, we'll have to show that this same region represents A intersection B prime. This is called B prime, and I'll address it as B prime. So we'll show that this same region will represent A intersection B prime. So from the definition of complement set, B prime or complement of B will be the region outside circle B. So this blue shaded region is representing set B prime. Okay. So now, which region is representing set A? This region, right? This circle represents set A. And when we have to figure out A intersection B prime, we will see that between set A and all B prime, the common region is this black shaded region, right? The common region between B prime and A is this, right? So since this is the common region of A intersection B, so this will represent A intersection B prime as well. So since this region represents both A minus B and A intersection B prime, so we claim that A minus B equals to A intersection B prime. So this is one type of method that we use to prove a statement that is true for set theory or an identity. Okay. So now we'll prove the famous De Morgan's law using another method. So there are two parts of the De Morgan's law for two sets. De Morgan's law also have a generalized version, and for two sets De Morgan's law is like this: A intersection B prime equals to A prime union B prime, and another part is A union B prime is equal to A prime intersection B prime. I'll show you the proof of the second part, this one, right? And after I show the proof of this part, you will try to solve or prove the first part by yourself. Okay? So at first we can remember that how do we prove two set equal? When we studied equal set, we knew that if we have to prove two set X and Y are equal, we at first prove that X is a subset of Y, and then prove that Y is a subset of X. And from these two statements, we can claim that X equals to Y. Here, let's assume this is X and this part is Y. Okay. So first we'll prove X is a subset of Y. Then we'll prove that Y is a subset of X. So at first we claim that X. We claim that A belongs to. Let's make it small c. Okay. C belongs to A union B prime. So it means that C is an element of A union B prime, and it is a representative element of A union B prime. So C doesn't belong to A union B. How do we get that? Since C belongs to A union B, this complement, so it must not belong to A union B. Okay? And see here that if C can be an element of A or B, if C belongs to A or B, it would belong to A union B. So C doesn't belong to A and C doesn't belong to B, right? So C doesn't belong to since C doesn't belong to A, that means C belongs to A prime, and since C doesn't belong to B, that means C belongs to B prime, right? So C belongs to both A prime and B prime, so we will claim that C belongs to A prime intersection B prime, right? Here we get that all of the elements of A union B, that were at X, will belong to AC intersection BC. That means Y. So we claim here that X is a subset of Y, right? This is a subset of this, right? And now we'll start from here. Let's assume C belongs to A prime intersection B prime. That means C belongs to A prime and C belongs to B prime, both of them. Then since C belongs to A prime, so C doesn't belong to A and C doesn't belong to B. And here see that since C doesn't belong to A and C doesn't belong to B, so C doesn't belong to A union B. So from here, since C doesn't belong to A union B, so C must belong to A union B prime. So from here, we say that this was Y and this was X. So we claim that Y is a subset of X. Since X is a subset of Y and Y is a subset of X, so we claim that X equals to Y. So from here, we claim that A union B prime equals to A prime intersection B prime. Okay, this is how we can prove De Morgan's law, and you will try to solve the first one by yourself. Okay, so now we have come to the last portion of this segment, and we'll solve some problem of generalized union and intersection. And as we can remember, what is generalized union and intersection? We say that if there are many sets, then to denote the union of all sets, we write it like this: union of AI from I to M, right? This denotes the union of all of these sets, and similarly this denotes the intersection of all of these sets. So this is known as generalized union and intersection. So if you are given a set where AI equals to 1, 2, 3 up to I, then you are asked that what is the generalized intersection of AI is equals to what? How can you solve it? At first, we can put 1 here in place of I. So the set will be equal to, starting from 1, it ends at I, and here I value is 1. So it will end at 1. So it will be a set with a single element. For A2, it will start from 1 and finish just in I, right? And since I equals to 2, A2 equals to 1, 2. Similarly, A3 equals to 1, 2, 3. So on. AN equals to 1, 2, 3, 4 up to M, right? So we are supposed to determine the intersection of AI. That means we have to find out those elements, all of which are there in all of these sets, right? A1, A2, A3, the common element of all of these sets. And here we can see that there is only one element in 1. So the only possible element that can be common to all of these sets is 1, and let's see if other sets have 1 as their element 2. Here A2 starts with 1, A3 starts with 1, and for any value of this I, always there is 1, right? So it starts with 1, always. So for all of these sets, the only common element is 1. So intersection of AI, starting from 1, I goes to 1 to n, the intersection is 1. So this is the solution of this generalized intersection, and I'll give you another problem to solve by yourself, and that is AI is a set where AI is like this, okay? And you have to determine the AI starting from 1 to n. What is it? What is the value of union of AI? Okay? So that's all from segment 5, and that's the ending of lecture 1. Hope you'll follow the Bangla contents and example classes, and I hope you will all perform fantastic in your next quizzes and assignments on set theory. Till then, thank you, take care.